The first question, I just highlight some of the mistakes you guys made, so that it's easier. Then I would have written them down in your scripts, so you can actually go and refer them. Okay, so the first question, right? I think the mistake that most of you made was you did not notice that the question highlighted standard temperature and pressure. Yeah, so because of that, I think a lot of you got 1 of the 2 marks because of this. Okay, so just make sure that you read the question carefully. I mean, quite rarely we want to trick you on this, but I also don't know why they decided to ask the students that. So that one is maybe really just to ensure that the students understand what information to take from the data booklets. Okay, so if you do the correct calculation, you will get 0.363. Yep. Okay. Then I think B part 1, a number of you didn't get it correct. I think it stems from the fact that you might not have learned this very well in JC1. I mean, it's understandable because this topic is not very easy, especially when you first entered JC. But just, I mean, I think it will be good for you to review this topic again before your prelim. Just a quick revision, or maybe a half an hour, 45 minutes kind of revision. In fact, this is in group 17. So I think you would have seen this in periodicity, but might not have gone through extensively. Okay, so the question actually asks you about boiling point. So for boiling points, I think the first thought process you need to have is to look at the intermolecular forces of attraction. Yeah, I think that is important for you to recognize, because if you don't, then it's not possible to do the question correctly. Okay, yeah, so basically to boil something, you need to overcome the intermolecular forces of attraction between the molecules. Yeah, so of course the next thing is you need to recognize that they are simple covalents. Okay, so because if you don't recognize that they are simple covalent, then again you're going to make a mistake. So simple covalent is something you need to be aware of. Okay, so after you recognize them, then it will be good for you to indicate the intermolecular forces of attractions between the molecules. Okay, so in terms of IMF, then I think you will be able to tell that HF will be hydrogen bonding. Okay, then for the rest will be dispersion forces. Okay, you can argue that is PDPD. Okay, but if you argue that it's PDPD, it doesn't follow the trend. If you know where I'm coming from. Okay, because for PDPD, right, you will expect HCl to have the greatest dipole as compared to HBr and compared to HI, but it doesn't really follow the trend of the boiling point, because the boiling point actually increases, correct? So this is the highest, HF is the highest, then HCl is actually the lowest. Then actually it increases to HBr, increases to HI. Yeah, so if you argue based on PDPD, you will not get this trend. Yeah, so the only way to argue it is to focus on the size and polarizability of the electron cloud. Yeah, so therefore focusing on dispersion forces. Right, so if you look at dispersion forces, you know that it is electron cloud size dependent. So the more polarizable, the stronger is the dispersion forces. So if you focus on that, then your answer will be correct. Okay, for these three. Yeah, but if you compare with HF is the highest. So you have to highlight hydrogen bonding. So in terms of the marking, right, how the marks are distributed is to recognize that HF has the highest boiling point because of hydrogen bonding between the molecules. Therefore, you need the most amount of energy to overcome. Then for the rest, the trend as follows because of the increasing electron cloud size and therefore increasing dispersion forces strength. Okay, I hope that will be okay. Hope that you won't make this mistake again, because this question come up relatively often, once in a while, in A levels. So that's why probably that's the reason why the school decided to test it. Okay. I hope that's okay. If you have questions, just raise. The contrasting part is part 2, which is on thermal stability. Thermal stability is a bit different. Thermal stability is related to whether the compound can decompose or cannot decompose. Yeah. So if they talk about thermal stability, right, then you want to focus on the strength of the HX bond. Okay, which is also in your notes. Of HX. Yeah. However, because it's 2 marks, so you can't just say that, oh, like the bond strength decreases. Yeah. You have to bring in the idea of the extent of orbital overlap between X and H. Yeah. So as the atomic radius increases from Cl to Br to I, then the extent of overlap is weaker. Okay, or you can say that you have a more diffused halogen valence orbital, so it will overlap more poorly with hydrogen. Something along those lines will get you the credit. Okay, so it's important to highlight this when you have this kind of question. Would that be okay? Yeah. Okay, so next I will want to focus a bit more on this IO3 minus, because actually quite a number of you got it wrong. So what I can do is, I mean the answer is here, but again, at the end of the day, it's not about the answers, because you can easily Google the answers, right? Yeah, so it's not about the answer. It's about the thought process in getting the correct answer. Okay, so the first thing you want to go about doing it, right? If let's say in JC1 it wasn't clear enough to you, is I think you need to look at the overall charge. Is there an overall charge? So if there is an overall charge, right? So that means that there is 1 electron from the external. Okay, I mean it could be from a metal, correct? Yeah, so it's just an electron from external source. So 1 external electrons. So that means that, right, when iodine is going to form bonds with oxygen, right, so it is actually 1 iodine. Okay, so the 1 iodine will have 7 valence, right? So this one no change. Yeah, and then my oxygen, right, it will be oxygen, 3 oxygen, right? One of them with 6 electrons, or rather 2 of them with 6 electrons. The third one have 7 electrons. Because the external electron will go to the more electronegative element. I think that is written in your chemical bonding notes. So if you want, you can go and flip over to topic 3. It should be somewhere along the pages where they teach you how to draw the Lewis structure, right? Yeah. So based on this, you make a decision in forming bonds, right, by looking at the number of valence electrons you are dealing with, if you know where I'm coming from. Yeah. So if you look at this, then you will know that in order for oxygen to be to have the octet configuration, then these 2 oxygen must share 2 electrons. Yeah. Then this one must share 1. Yeah. So if you solely make that decision based on this, then you will be able to come up with this answer. Okay, I'm not going to draw it out again. Yeah. So you will be able to come up with the answer where I'm sharing a pair here, and then the other oxygen is simply a single bond. Yeah, and then of course it will have a lone pair of electrons here. Yeah, because what most of you did was, the common mistake was usually you do a lot of dative bonds or you do a lot of double bonds, but it doesn't necessarily work that way. Yeah, so you have to be a little bit careful when you sketch your dot and cross diagram. Would that be okay? Yeah, so just be aware of this, because I thought that actually it's a common mistake made by a lot of students anyways. I think not just you all, but I think in general the students still have a bit of difficulty in drawing dot and cross. That's why we test it sometimes. Okay. Okay, so based on that, you can easily answer the VS-EPR. So I don't think I need to discuss VS-EPR with you guys. Okay, so solely based on that, you can easily answer the VS-EPR theory. Why is it that it takes on a certain shape. Okay, so I think even if you have drawn this wrongly, you will have gotten this correct. So I don't think you guys have any issues on this. Okay. Okay, so the big issue comes when it comes to the disproportionation part. Yeah, because I think you are still balancing equations solely by looking at the atoms, material balance. I think I mentioned to you. I think I mentioned to you all before. I think in JC1, the best way to balance equation is really to look at electron transfer. I think we talked about that lah. So I think I also wrote on your scripts, either asterisks or what. So what actually is the best way to answer this question? I think I can sort of illustrate this to you, because they highlighted that you get IO3 minus and I minus when you have disproportionation of iodine. Okay, so first of all, right, the easiest way is you write iodine. Okay, then you leave a bit of space here. Okay, then you draw an arrow. Okay, then you draw the two products. So the one of the products is I minus, then the other one is IO3 minus, right? Okay, then of course the next thing you want to do is you want to ask yourself, what is the oxidation state? So oxidation state of iodine, of course, is 0. Okay, then the oxidation state of this is -1. The oxidation state of iodine here is +5. Yeah, so that become interesting because you know why? It is a bit like one of the iodine become +5, the other one become -1, which is not possible, right? I hope you agree with me on that. Because let's say there are two persons, I give, or rather me and another person, right? I give that person one apple, then I will have one less apple, he or she will have one more apple. So that it doesn't work that way, correct? In this case, yeah. So therefore, one iodine molecule itself will not work because one of the iodine will have to become +5. So therefore, right, you end up with a situation where one iodine, right, will need to lose 5 electrons. I hope you know where I'm coming from. So one of the iodine will need to lose 5 electrons to become +5 because it needs to become +5. Okay, then this 1 electrons, right, will have to be gained by the other 5 iodine. Correct? Yeah. So based on that, the total number of iodine I need is actually 6. Yeah. Then only one of them become +5. The remaining one will become -1. So that's why the ratio is 3, 5, 1, which is something a lot of you didn't get. Yeah. So based on this, they say alkaline medium. So alkaline medium, I need to balance the overall charge, right? So I need to add 6 OH minus on the left hand side. And then after that, I need to write out the water. Okay, so this is the way to balance it. You can balance it from an easier method which you learn in JC1, which is to do them one by one. You know what I mean by one by one, right? One by one means I write out the reduction half equation first, and then I write out the oxidation half equation, then I combine the two. But I told you before in JC1, if you do it like that, it's faster. So you can try doing it this way, if that helps. Okay, Ken? Yeah, I mean, let me know if you have issues. This one will be a pattern recognition, which I think you guys often get in our school exam. So I think probably needs no introduction. So how to go about getting it correct? Just recognize the pattern. How do you know where the arrow goes? Okay, so I think you need to look at the product. So you notice that CA and CB both become double bond O, right? And you are aware that eventually you get HiO3. And how do you draw HiO3? Again, it will need no introduction because you know the structure of IO3 minus here. Correct? Okay, assuming you drew it correctly, that is. Actually, you notice that over here it sort of gave the game away. What is the structure of C part 1? I don't know whether you recognize that. It sort of gave the game away. Because based on IO3 minus, I can actually draw my structure here. So double bond O, and then OH. Like that. Yeah. So let's say I don't know how to do this part, right? I can actually guess the structure based on intermediate B lah. Not entirely, but roughly. Okay, so the arrow flows this way because over here, I need to gain a CO double bond. Okay, then this arrow is correct because I need to gain a lone pair over here. Yeah, okay. So the arrow point, the way the head is pointing is very important. Okay, Ken. Hope everything is okay. Yeah. Okay, then the hybridization one, from the marking, I can sense that it's not too bad on the whole lah. But by and large, it's about comparing between percentage or S character of sp3 hybridized carbon. I think it's about glycol A and ethanol, right? So glycol A is over here. So glycol A is sp3 and then ethanol is sp2. So you look at percentage of S character. Yeah, but when you highlight the percentage of S character, right, it will be better if you can highlight the effectiveness of the overlap between the sp2 carbon and H. The reason why that is the case is because you want to say that the greater the percentage of S character, right, then on the average, the bonding electron pair will spend its time closer to the nucleus of carbon. So you either highlight this or you say that the overlap is more effective lah. So it's up to you how you want to craft your answers. Okay, yeah. Any questions? Yeah, okay. So part 3, again, you saw this kind of question before. You also notice that a lot of the JC, they try to imitate or mimic the kind of question that Cambridge asked. This one, they ask you to do the overlap, right? Okay, so when you draw a nice orbitals, ultimately you need to do some labeling lah. Correct? I think some labeling actually helps a lot. Yeah, labeling in a sense, I also need to know which belongs to the O, which belongs to the carbon, right? Because some of you hide the answer without labelings. Yeah, then I also need to know what are the bonds you have indicated lah. So for example, this indicates the sigma bond, right? So this is the head-on overlap, okay, between sp2 of Ca, okay, and sp2 of oxygen. Yeah, just highlight directly, like it's head-on overlap, or you can say head-on overlap to form sigma bond, but okay, I mean if you want to be more explicit, you can say sigma. Okay, then for the other one, you can highlight this one. It's actually the pi overlap or side-on overlap. Okay, between 2p of Ca and 2p of O. Yeah, so just highlight directly. I think it will help a lot when you want to explain the answers lah, because they actually ask you to draw a labeled diagram. So I think you need to give some labels and annotations. Okay, yeah, okay. This one, some did, some can do, some cannot do. So again, what is the issue lah? I think the issue is about pattern recognition. You'll notice that the role of Hi4, right, okay, is to split alcohol with 2 adjacent hydroxyl group. I think this is very important. You need to know the chemistry behind this, okay, is to split the alcohols. So therefore, right, when I draw my C, I must have 2 adjacent alcohols, correct? 2 adjacent alcohols, right? And then after they split, the 2 carbon with the alcohol must become ketones or aldehydes. That was what is being reflected here, correct? Yeah, so based on this alone, the first thing I need to do is to find out where are the aldehydes and ketones. So you can find out the aldehyde. So this is the ketone, then this is the aldehyde, right? So therefore, because they are still in one molecule, so originally there must be a ring joining these together. Yeah, and then of course numbering the carbon helps a lot, correct? Yeah, so if you try to number, if you try to number the carbon, then this will be 5, right? 5, 4, 3, 2. Oops, sorry. Sorry, I think it's the other way. Oh no, sorry, it's correct. Yeah, correct, it's correct. 5, 4, 3, 2, then this is 1, right? And then after that, based on this numbering, then this will be 6, 7, 8. Oh, sorry, the other way around. This will be 8, 7, 6. Yep, so they will cleave here, and then you will get the product. Yeah, so read the information in front. The two glycol must be, the two alcohol must be side by side. Yeah, then there's only one answer here. Yeah, so it doesn't affect the OHs. Yeah, so with that, I think that would be straightforward lah. But of course, if you can do, cannot do, then just move on lah. Yeah, I think similar to what you get in some of the other questions in the A levels, right? Yeah. Okay, Ken, any questions for this? Then this nucleophilic addition is the last part. I think the learning objective needs to be in. So again, for nucleophilic addition, remember that your potassium hydroxide is actually an ionic compound, so there shouldn't be a covalent bond. And you can actually show the generation of H plus and Cn if you wish to. You can simply just write this. Of course, if you want to highlight the role of the traces amount of OH minus, then you can simply just write acid-base reaction between HCN and OH minus, so you get Cn minus. Yeah, then the Cn minus generated will then perform nucleophilic attack, and then the rest. Remember to put your slow step. Very important. Okay, Ken. Yeah, so that will be the end of the first question. Any questions? Okay, if no, then we can move on to question 2. Yeah. The first question actually, if you ask me, amongst the few of you, right, not so well done. So that's why I said to some of you, good to review your GC1 stuff. So I mean, it may be an easy question, but still requires a bit of attention if you need to lah. Okay. Question 2, easier. It's actually easier than the rest, so-called lah. So I think I will just skip some parts. Okay, 2A1 just assumption. So make sure you highlight the assumption properly, like volume of gas molecules negligible as compared to volume container. So it's the gas particles or gas molecules, but not the gas alone. Then negligible intermolecular force attractions, and then perfect elastic collision between particles lah. Okay, Ken. So I think that is fine. Part 2, PV over T. Oh, so this is ideal gas. Okay, then they show how it varies the temperature for 1 mole of NO2 at a high temperature. Okay, so you have to read it carefully. The question asks you to sketch at a higher temperature. So remember this, it's at a higher temperature. Yeah, label as A2. So we are looking at a higher temperature, not a lower one. So at a higher temperature, intermolecular forces of attraction between the molecules is overcome. Okay, why then? Why is it overcome? Because they possess greater kinetic energy. So that needs to be also part of your answer. Okay, so it is the greater kinetic energy that is present that leads to I mean, of course, if you want the answer in full, okay, the greater kinetic energy is present by the gas particles is able to overcome the intermolecular force of attractions between them. So in this case, it will be PD. Okay, or you can say ID, or you can say dispersion forces. I think it doesn't really matter here. Okay, yeah. Then after that is followed by a simple, relatively okay kinetics question, I hope. Okay, so they gave you experiments. With different initial concentration. So you notice that the initial concentration of NO2 is always much higher than that of HCl. It is done deliberately. Why is that the case? Because they want to make it a pseudo-order reaction with respect to HCl. So remember, we always want one of the reactant to be of a much higher concentration, so that the change in its concentration will not affect the rate significantly. Okay, can? So they give you a graph, then of course your idea is really to draw the best fit, right? Sorry, not best fit, to look at the graph and then determine the half-life, if any, and then draw the tangent at time equals 0. Okay, so I will just skip this. I mean, most of you did quite well. Okay, so for part 1, they ask you to calculate the mole fraction with reference to figure 2.2 present at t equal 200 seconds. Okay, so what you need to do is look at 200 seconds, go to 200 seconds, look at the concentration of NOCl. Okay, so I think if you read off the graph, carefully, you should get experiment 1 at t equal 200 seconds. Okay, so if you read off the graph carefully, it should be 0.032. It's over here. Okay, I think you can just read off the graph. Because I gave you the A4 copy, so I think you can easily get the data. Okay, so this is the point 0.03. Oh, sorry, I think the slide is not working. So 0.03. Okay, can, yeah. Then happens to be the plotted points as well, but yeah, you can just read it off. And then after that, based on what you have at equilibrium, what you understand, sorry, not equilibrium, what you understand by the reaction, you can simply just calculate the final concentration. Yeah, so this is based on the fact that, okay, if I have 0.032, then what is the change in the number of moles of HCl? So that will be minus 0.032. Then the final one will be the difference between 0.05 and 0.032. Yeah, and then NO2, remember the times 2. Yeah, so you probably need a table similar to ICE table, but not really an ICE table. Yeah, then from there you can determine the mole fraction by simply just summing up everything else, right? And then I think you will be able to get 0.031 or 0.0314 for that matter. Okay, can. So some of these molecule calculation, they often test it in your exams. So just make sure you know how to do it, especially practicals. Okay, yeah. Then total pressure, you will make use of PV equals nRT. So again, it's a direct application. Of course, you need to be a bit careful because the volume is in cubic meter. So you need to do a bit of conversion. Okay, because over here, okay, what do I mean? Because over here, right, the volume, the concentration is in mole per dm cube. Yeah, so when you want to scale accordingly, you have to scale to cubic meter. So you need to remember that. Okay, so that is very, very important when you are doing the question. So you have to be very careful. Yeah, so number of you got it wrong or get weird numbers, etc. is really, really because you didn't scale. Okay, generally when you get a pressure, right, that is very, very low, then you know something is wrong. I hope you understand that. Because our atmospheric pressure, right, our atmospheric pressure is about 1 bar, right? That's 10 to the power of 5 Pascal. Correct? That's atmospheric pressure. Then if you get like 1,000 times lower, then something's wrong. Because it's actually quite hard to have such a low pressure, even in laboratory conditions. So you have to be a bit careful. Yeah. So normally, although it's theory, right, we will try to make sure that things are closer to reality, so cannot be such a low pressure. So just check whether you anything missing in your working. Then if you check carefully, then it should be fine, usually. Okay, can. Any questions so far? Then part 3, Using figure 2.2, okay, so this one is okay. I think generally well done. So I will skip because I think you guys have done it very quite often already Should be quite good at it. Deduce the order. So basically draw the tangent at time equals 0, and then you should get order of 2 for the case of NO2 Okay. Then the final concentration of NOCl if the reaction were to proceed to completion, right? How do you do this? Very straight. Okay, the most straightforward thing I can tell you is you look at the initial concentration of HCl because this is the limiting reagent, correct? And then HCl to NOCl is a 1:1 ratio, right? Yeah. So when all the HCl reacted, NOCl will be same concentration. Yeah, that's about it. Yeah. Okay. So although they did not need you to explain, but based on that, you should be able to tell. Okay, and then all the reaction respect to HCl, I think this one I just find tangent. Sorry, not tangent. Half-lives, right? So from the graph you can find a half-life, which remember I think I also mentioned to you in tutorials before. Show your construction line, how you find half-life. Okay, yeah, I think this should be fine as well. And then after that, you can move on to part 6. Part 6 is an interesting part. Okay, if you take note of it The half-life of the reaction in experiment 2 was found to be 540 seconds. Okay, 540 seconds. Earlier on, you find your half-life to be about 135. Okay. They say experiment 2 is 540 seconds. Okay, experiment 2. So experiment 2, you have concentration of NO2 0.5, HCl 0.05. Okay, so remember that. And then they ask you how the half-life of the reaction in experiment 3 will compare to that of experiment 2. Yeah. Okay. Now, if I scroll back again, you notice that for experiment 3, right, initial concentration of NO2 remains the same. So it's in excess. Correct? It's in excess. Right? Initial concentration of HCl reduces from 0.05 to 0.01. Okay? Yeah. Then, what do you learn about half-life? Half-life is not concentration dependent, right? Because half-life is ln 2 over K, correct? For first order reaction, T half is ln 2 over K, right? Yeah, so because of that, it doesn't matter whether my concentration of HCl is 0.05 or 0.01. Yeah, so it will not affect half-life. So therefore, you have to incorporate that idea into your answer. And of course, to highlight that NO2 is in excess, because that is actually quite crucial. But of course there will be benefit of doubt if you don't say that, then I think we understand where you're coming from. Yeah. Okay, can. Yeah. So in case you're curious, if you want to write out the full version, so the rate law in this case is actually K prime HCl. Okay. Then K prime is actually K times NO2 Okay. Then what you know is T half is equals to ln 2 over K prime. Okay, and it's ln 2 over K NO2. Yeah, so you notice that the dependency factor is on NO2, not on HCl. Because NO2 is in excess in this case. Yeah, so it substitutes into the experimental rate constant, which is K prime. Okay, yeah. So I think that should be fine. Okay, for C, you work on it based on what you know. So okay, so write an overall equation. So you just add all the equation up. Then you notice that anything on the right will cancel anything on the left. So these two will be cancelled. Okay, so this will be cancelled. Yeah, so essentially is that. The type of reaction is not free radical substitution. It's more of an addition reaction. If you notice, it's an addition reaction. Correct? Because you destroy the CC pi bond, right? And then you sort of add across the pi bond with the NO2. Yeah, but because it is not based on electrophile, so it's actually called free radical addition. But you don't have to call it free radical addition. You can just call it addition. But of course, this name you have seen it before, so it's free radical addition. Okay, yeah. Okay, can. So far, any question I can take, or everything's okay? Because you all have been quite quiet. Okay, then question 3. Okay, question 3. I noticed, and I told you before in class, quite directly, that this topic will be your weakest link. Turns out to be true, right? Because actually quite a lot of you still cannot do this topic. I mean, I'm not trying to be a jinx or what, but okay, so even in the past, the old curriculum, if you have elder siblings to A level before 2017, right? Yeah. The physics students usually have issues with this topic called nitrogen compounds. And back then, nitrogen compounds also incorporate some protein stuff. Yeah. Then after that, they took out all the protein stuff, but a lot of schools still test it. But that's because Cambridge sometimes also tests it. So it's not that the school wants to kill the students. Yeah. But if you ask me, right, this topic is really not very difficult if you study well. But you need to remember one or two things. Can I say? I don't want to say a few things. It's really just one or two things, which I also mentioned to you guys in tutorial before. Okay, because a lot of the information, right, is given to you. You know what I mean? It's given to you. So what you need to do is just to process them. Okay, Ken, so I will just start off directly. I mean, I won't go and read through the story because you know that I need to use table 3.1. Okay, so first of all, right, they gave you something called heptapeptide. I knew hepta is a difficult name, but hept actually means 7. So it contains what we call 7 amino acid residues. That is the term people use in bio. I know none of you are bio students, but I just tell you the terms so that at least when you learn chemistry, you're also familiar with this term. So there are 9 amino acid residues. So they say that they actually heat up with sodium hydroxide. Then this is what we call a partial hydrolysis. Okay, so they partially hydrolyze the peptides. Okay, so the partial hydrolysis eventually give you a mixture of dipeptides. Okay, so this is it. This is not important here. Yeah, not important here. Okay, so after that they recognize that they got this two instead of they got this two glutamic acid instead of this. Okay, so if you try to go back GLU instead of glutamine, right? You notice the difference between them is that for glutamic acid, the side chain is a carboxylic acid but for glutamine, right, the side chain is like amide. Yeah, but it wouldn't come as a surprise, right? Wouldn't you agree with me? Because I'm heating it with sodium hydroxide, then the amide will be hydrolyzed. So all you need to say is that the glutamine is actually hydrolyzed, or the best answer, of course, glutamine undergoes alkaline hydrolysis to give glutamic acid. And then upon acidification, or rather, glutamine undergoes alkaline hydrolysis to give the conjugate base of glutamic acid. Then upon acidification, then glutamic acid is obtained. That's all. That's all you need to say. Okay, you can say it in any way you want, as long as that meaning is clear. Would that be alright? Okay, can. So we just focus on the key things. Okay, then they also mentioned that SERTYR, okay, serine, tyrosine is one of the group. Okay, so again, I told you before in tutorial, right? When you draw from the N to C terminal. Okay, so of course, the student wrote it nicely here, N to C terminal, right? Yeah, so just draw from N to C terminal. Yeah, no need to ask any question. So basically, use the data here. Which one start first? Serine, right? Yeah, serine. So you look at serine, which is the one with the side chain alcohol, and then tyrosine, which is the one with the phenol. Yeah, So you just draw from N to C terminal. Okay, so maybe it's a bit faint, so it's NH2, CH, then CH2OH. Yeah, then make sure that because it's pH 13, right, your carboxylic acid is deprotonated, your phenol is also deprotonated. Yeah, so that's all they want from you. Okay, can? Yeah, so make sure you draw from N to C terminal and start from serine. N terminal of serine, N with the C terminal of tyrosine. I think we did this in tutorial a few times, so just take note of it. Will that be okay? Okay. I think we also did this in tutorial before. Just that maybe that time y'all were very stressed. Okay, actually to do this, right, all you need to do is to do some overlapping. Okay, let me try to explain to you. Is to find something that is common in all the 4 chains. Okay, easiest way I will do it is to write it out in a way where there are overlapping patterns. Okay, so TYR, SER, PHE, ARG. Okay, then after that, right, you try to see whether there are only overlap. Okay, so there's an ARG here. Okay, and then SER, right? Okay, so maybe I write it here. ARG, SER, TYR, SER. Okay, no, let me highlight one thing. I may be wrong. Okay, I need to tell you, I may be wrong, but I just write them out first. Okay, because at the end of the day, during exam, right, you must try until you get the correct answer, correct? You don't just stare at it. Yeah, and then after that, I look at this LEU, ARG, SER, TYR, SER, LEU. Okay, so you notice that over here, right, there is something that you need to go and find the overlap. Correct. Where is the likely overlap that you can find from here? Okay, correct. Now, and then of course another thing you might notice is that when I look at this, okay, wait, let me just bring this out. Okay, there is this interesting overlap. ARG, SER, TYR. ARG, SER, TYR. Correct, right? Right. So therefore, right, can I try to do an overlap with these 2 fragments first? Yeah, that means my initial starting point is not so correct. Okay, but never mind, because we all make mistakes when we try to do things, right? Yeah. So I mean, so it's okay lah. I mean, if we make mistake, we just admit it and then we move on lah. So I mean, that is how we learn, right? Correct. Okay. So in that case, I'm going to write the LEU here. So I'm going to write it below. Okay. So I'm going to cancel this first. Okay. ARG, SER, TYR, right? Okay. And then I'm going to write LEU here. Okay, can? Then, okay, I'm going to look at this final fragment. Okay, and then I notice that there is an overlap here. TYR, SER. Correct? TYR, SER. TYR, SER. So TYR something. Then I'm going to write that fragment here. So TYR, SER, PHE, ARG. ARG. Yeah, then after that, I'm going to count, right? So I have 1, 2, 3, 4, 5, 6, 7. So which is a heptapeptide. Yeah, so my answer will be LEU, ARG, SER, right? SER, then TYR, SER, PHE, ARG. Yeah, so it's a bit of a try and error. So key idea of doing this question is to find overlaps. Yeah, so again, it's not about the answer, but it's about how you come up with the answer here. Okay, can? Yeah. Okay, so part B, part 1, we have done it many times. I don't think I need to elaborate. But I want to say one more thing in terms of the phrasing of your answer. For nitrogen here, we are talking about the lone pairs of electrons on the nitrogen. You don't talk about negative charged. Some of, not only you but some of the students' script I mark for other kind of questions. You have to be a bit careful. Are you talking about electron densities or are you talking about negative charged? In this case, clearly is on electron density around the lone pairs of electrons on N. So you don't talk about negative charge, because if you talk about negative charge, it's very difficult to give you the credit because it's actually not correct. There's no charge here. Yeah, okay, can. So we talk about increasing electron density over the nitrogen then to make it more electron rich and then therefore stronger base. Okay, can. Then over here we have equilibrium between the ions and water, so ion dipole interaction. When they say predominant interactions here, they mean intermolecular attractions between species. Or you can say interspecies interaction, but usually we don't say interspecies, so it's intermolecular force of attractions. So it will be ion dipole interactions. Okay, then the stronger the interaction, the better, right? Because it releases more energy. So the larger the charge density, the stronger the attraction. So that is the highlight of part 3. Okay, so you decide which one has a larger charge density. Both of them same charge, so which one has a larger and on the average cationic radius. So of course the one that's more bulky will have the larger cationic radius. So therefore weakest charge density, lowest charge density. Yeah, so I'm expecting the conjugate acid of methylamine to form the strongest ion dipole interaction with water. Okay, so that is what you need to look out for part 3. For part 4, they ask you why the pKb of this is lower than this in aqueous solution. You notice that this is an interesting question, right? Correct, because it does not agree with the explanation you gave for B part 1. Do you all notice? It doesn't agree, right? So methylamine is actually a stronger base. Yeah. How do you tell? Equation 3.2 tells. Okay, then how do you answer that? Yeah. So you answer that by focusing on the fact that my conjugate acid of methylamine is better solvated. Yeah. So because it is better solvated, right, I expect the POE of equation 3.2 to lie more to the right as compared to 3.1. Yeah. So if it lies more to the right, that means that on the for the same concentration of trimethylamine versus methylamine, right, I'm going to get a higher concentration of OH minus for methylamine. Yeah, that's why the pKb is lower. So that is what is being reflected in the answer. You notice that the question guide you to get the answer, not the other way around. Yeah, they do not ask you for the answer simply by by asking you to suggest from the air, but they give you some data. Okay, can. Hope that's okay. Okay, then next you have this antigen test kit, which is a protonated trypsin. So again, 3 alcohols. The N over there is not an amide. It looks like amide, but it's not, because there is a CH2 separating the carbonyl carbon and NH2. Okay. Then question asks you draw the structure, explain why high melting point. So again, you have to show the Zwitter ion. Why is it high? Why does it have high melting point? Because it can form strong. The Zwitter ion can form strong ionic interaction. Okay, between the particles. Yeah. So remember this, when you draft your answer, it will be good that at the beginning highlight the electrostatic force of attraction as ionic bonds. Although the answer, of course, is mentioned later on. Yeah, but it will be good to highlight it at the beginning rather than at the end. Okay. Yeah. Then I'll move on to acid base. So for acid base, some of you still struggle a bit, then some of you okay, but at the end of the day, how do we go about doing that? Okay, so first of all, calculate the concentration of sodium hydroxide you need to prepare this buffer, right? Yeah. So again, you are given 1.1 mole of solid trypsin, and then in 1 dm cube. of aqueous sodium hydroxide. Okay, so I need a buffer. What is the buffer? The buffer's pH, sorry, what's the pH of the buffer? It's given to be 8.78. Yeah, so again, the preference is up to the student. Right, I mentioned in the tutorial before, right? If you like to use the Henderson-Hasselbalch equation like this, you can use it. No problem. Yeah, but if you don't really like to use it, it is fine also. Okay. Why is it fine? Because number one, right, you are given the pKa, correct, which is 8.15. You're given the pKa, right? Yeah. So at the end of the day, this question it can be simplified by saying that, okay, I am just using the Ka2 value. Okay, I'll write it out first. Then T minus, okay, over H over TH. Okay, because I am given the pH, so concentration of H plus can be determined. Okay, I am given Ka2. Okay, I'm not given Ka2 per se, I'm given pKa2, so that's 8.15, right? So Ka2 will therefore be 10 to the power of minus 8.15. Yeah, so therefore I can find out the ratio between these two, T minus and TH. Yeah, and finding out the ratio is very important, because when you find out the ratio, then you can easily solve for the concentration of T minus and TH as and when you want, correct? Which form the premise of solving this question. Okay, can. So I'll just guide you to here. If you want, you can just write out the answer, which is 0.0810. Other than that, I think shouldn't be too difficult to solve. Okay, can. Yeah. Then here we asked before in our consolidation exercise, how a more dilute buffer solution will compare in terms of buffering capacity. Okay. Okay, so basically you need to highlight the important thing about T minus and TH. Okay. You need to highlight that because I have less of them, right? Okay, then less of them to actually react with the small amount of H plus and OH minus added, which will translate into a greater percentage of change in their ratio. Yeah, then therefore I will expect the buffering capacity to be lower. In the past, in tutorials, right, I use an example to explain to you all before, so I can use it now. Okay. The example I use is just a random example using randomly gotten numbers. So for example, right, let's say my T minus to TH, right? For example, let's say I have 100 over 100. So the ratio is 1. Okay, correct. Now, imagine that I add 1 H plus. Okay, so if I add 1 H plus, then what's going to happen is that T minus will drop by 1, TH will increase by 1, right? Yeah, so now the ratio goes from, now the ratio becomes 99 is to 100. Okay, which actually not much change, right? Because the change is from 1.0 to 0.99. So it's a 1% change, correct? Yeah. Then let's say, right, now my ratio, right, is just made of 10 species. Okay. Then if I add 1 H plus, minus 1 plus 1, right, I'm actually getting 9 over 11, you know. Sorry, this I think I wrote, this is 101. Yeah. Then of course, this will not be 0.99. So let me take a calculator. So it's 99 divided by 101. I think it's slightly less than 0.99. Okay, I just calculate 99 divided 101. Okay, so it's 0.98. So it's 0.98. Okay, yeah. Then 9 divided by 11 is a different ballgame, right? It's 0.82. Yeah. So I hope this is a good illustration for you. Although the ratio of the conjugate base to the acid is the same, right? Both are 1. Yeah. But the one that is more concentrated has a stronger buffering capacity. Okay, because if I add one equivalent of H plus, right, the more concentrated one only dropped by 2% in terms of ratio, but the less concentrated one dropped by 18%. So you can use this example to help you answer this. But you are not supposed to calculate. So you write in terms of the idea of the larger change in the ratio leading to the reduce in buffering capacity. Okay, will that be alright? Yeah. Okay. Part D question asks, the deprotonated trypsin was titrated with this. Calculate the pH of 0.1 mole of the trypsin at 25 degrees C, right? Okay. Acid-base equilibrium again, right? This is simply the conjugate base, right? Right? The salt in that sense. So at equilibrium, what happens? It undergoes hydrolysis, right? To give HT plus OH minus, right? Yeah. So again, same thing. We probably just need an I stable, right? So it's 0.1. So dash dash dash. Then minus Y plus Y plus Y. So 0.1 minus Y. So this is Y, right? Correct. Yeah. Then what is the KB? KB1. So do I know pKa2? Yeah, so pKb1 is associated with pKa2, 8.15. Yeah, so in this case, the Kb essentially is 10 to the power minus 5.85. Correct? Yeah, because it's 14 minus that, so it's 10 to the power minus 5.85. Yeah. Okay, so you calculate Y, and then after you calculate POH, and then you calculate pH. So calculate Y equal to this, POH equals to this, and then pH. Okay, I'll just give you the answer. It should be 10.6. Okay, can. Then for that, all you need to do is just to write out the numbers. Yeah, and then the volume you need. Okay, because the concentration of the acid and the base is the same, right? Yeah, so essentially you need 10 cubic centimeters for the first neutralization. So this will be 5. Yeah, and then after that you will need 15 here, and you can't get the last endpoint because the last endpoint will not be obvious. Yeah, but it doesn't matter. This is just theoretical. Will that be alright? So to some extent, students should be able to fill this up if you concentrate on this. Yeah, but I know sometimes it can be very confusing when you're doing acid base. Okay, it's understandable. Will that be alright? Okay, and then the indicator is okay, just methyl rate. So methyl rate, how do we work based on how do we look at methyl rate? Methyl rate basically indicator is a standard explanation. You just need to ensure that rapid pH change at the I mean the use of methyl rate because the indicator color, right, color change, right, happens to coincide with the first rapid pH change, so which is here. So I think you mentioned that, then that will be fine. They usually tell you color extreme of the color indicator of extreme situation. So very acidic, red, alkaline, near to alkaline, or alkaline will be yellow. So pH change, it's not yellow, it is not so much of red to yellow. Oh, sorry, yellow to red. Okay, but it is more of yellow to orange because you have to indicate the intermediate color. Yeah, okay, can. Yeah, so just be a bit careful here. And then the second indicator, second endpoint cannot because there's no region of rapid pH change. In fact, there is no change, not much change. You won't see much change there. Okay, then then the N2O4 okay, no, this one I don't need to explain, right? It's a recall question, mode of action of catalyst. And then this portion will be equilibrium. Am I right to say that? Will be some form of I mean, some application of, because first they ask you to write expression, right? To write expression for NO2 in terms of, yeah. So if you shift the thing, when you shift NO2, when you make NO2 as the subject, right? Actually, it's a square root, right? Yeah, so you have to be a bit careful. So in terms of Kc, so equals to square root Kc, yeah, N2O4, something like that. Okay, can. And then oh, sorry. I think I put this page at the wrong side. Yeah, just now you didn't tell me. Okay, so this is actually page 12, right? Because I think I skipped a page in the earlier question. Yeah, it's actually from 11. So I thought I finished here. Yeah, okay, never mind. Anyway, that was the earlier question. I think we are done with the acid-base one. So I think I swapped the page around. Okay, so anyway, for page 12, if I were to continue, okay, from where we stopped earlier on, yeah. So yeah, it'll be like that. And then after that, you use the answer to C part 4 and the mechanism given in figure 2.3. Figure 2.3, if you remember, okay, if I go back to here, right? Figure 2.3. The slow step actually involve CH2 colliding with NO2. But NO2 actually comes from N2O4. Yeah. So in that sense, right, you have to represent NO2 concentration in terms of N2O4. So that was the purpose of the earlier question. Okay. So if I were to shift forward to this, then I'm just going to continue from here. So it looks a bit stranger. So the rates is actually equals to K, actually it's NO2, and then the alkene, right? CH2, right? Yeah. Then basically what I need to do is just substitute into here. Yeah, then that will be my answer to part 5. So eventually I'll get K prime N2O4 to the power half, and then CH2, and then you can define K prime for me. So K prime essentially is K prime, yeah, wait, Kc, square root Kc, like this. Okay, can. Yeah, so I think I skipped this page because I think I was rearranging the pages earlier on. Yeah, I didn't notice that this was skipped. Okay, any question before I finish with question 4? Okay, okay. For question 4, you have phosphine. You are given this thing called phosphine, triphenyl phosphine, but short form is called phosphine. Okay, exists in equilibrium. One is tetrahedral, the other one is square planar. So they tell you that it's a different color, and then delta H, they ask you for delta H, so I think you can deduce from the color, right? Whether Y in 4.1 has a positive or negative value. Okay, so when you increase the temperature, it become the proportion of G to F increases lah. So there's more, become more blue lah. Yeah, okay. So POE shift to right, so therefore there are H positive. I think no issue. Okay, just make sure you highlight the important points. Electronic configuration, remember, you remove electrons from 4s first. Okay, can. So just make sure you write out the correct electronic configuration. I mean, that's all I can say. And then square planar complexes and tetrahedral complexes, they are arranged a bit differently lah. So normally in exam, if we want you to know how to arrange them, we'll just give you the boxes to fill lor. So 8 valence electrons, they are 3D, right? So we just fill them in accordingly lah. Then you notice that the tetrahedral complex is the one with 2 unpaired electrons. Okay. They ask you to draw x squared minus y squared. Contextually, this question asks you why F has the highest energy. Okay. When you explain, don't give a generic explanation. Means don't say things like, oh, you know, in general, orbitals lying along the axis will be repelled more because your ligand approaches it from the axis. Don't give a generic explanation because the question here is not generic. Asking you specifically why the 3D x squared minus y squared has the highest energy. So you have to highlight that in the square planar complex, the ligand approaches from the x and y axis. Yeah, you must highlight that. Yeah, and not give something generic. Yeah, so it's only when you highlight that you will get the credit. If you give something generic, you might not get the full credit. Remember that. Okay, Ken. The paramagnetism thingy, we have discussed it in tutorial before lah. So I think, and anyway, they are not asking you lah. They are just asking you to draw the distribution of electrons, right? And then after that, they ask you why F and G have different colors. Then again, the highlights is that for F and G, they have different electronic configuration. We are talking about the electronic configuration at figure 4.1. Not the generic electronic configuration. Yeah, so we are talking about the fact that the electrons arrange themselves differently in the 3D orbitals. Yeah, so because of that, the energy gap is different. What do I mean by the energy gap is different? You notice that for tetrahedral, we are looking at this energy gap, right? Then for the case of the square planar complex, we are looking at this energy gap. Yeah, so they are a bit different. So because they are different, then you expect the electronic transition, the electrons to be promoted to the upper set of the orbitals, to require different amount of energies, right? Because of the different in the energy gap. So absorb at different wavelength, etc. Okay, Ken. So I think that needs to be highlighted in the answers. Yep, and then they said H is the cis isomer of F. Ask you to draw cis isomer, okay? Then you can just draw it in, and then YG converts to F rather than to H lah. So again, if you put the two bulky groups, there will be unfavorable steric repulsion. So they prefer to be trans to each other. Yeah, I think we have discussed something like that before. So I think it shouldn't be a major issue to highlight this. Okay, I think the transition element question here, I suppose you guys should be able to do it quite well, because I think we have done enough in the class. But again, I mean, sometimes you just need a bit of additional different scenarios to help you improve, right? Okay, part B. They say that my waters from copper mines contains copper 2. Okay, and then to separate copper 2 from the other impurities, organic acid dissolved in oil is mixed. Okay, key word here, you might not recognize, is organic acid dissolved in oil. So it's HX oil. Okay, that's a keyword. And then HX react with copper 2 to form this, which is soluble in oil but not in water. Okay, very important. They ask you what is the feature of the ligand that enables UX2 to be soluble. Don't answer the reverse. Don't say things like, okay, non-polar is correct. Cannot form hydrogen bond in water, also correct. But why not you highlight the positives? Meaning, X being non-polar will be able to form favorable dispersion forces with non-polar oil molecules. So therefore, it's soluble. Something like that. Yeah, talk about the positive parts, not the negative parts. Okay, usually that is the idea that we want to highlight, see from the students. Okay, yeah, then they give you this graph on the absorbance. This is called calibration curve. If you remember, the planning question, consolidation exercise I gave you guys, 2013 paper, A-level paper. Yeah, that one is on copper 2. Yeah, so same thing. This is called calibration line. Okay, can revise that for your planning as well. Okay, so based on that, then they ask you absorption 0.82. So what is the concentration of CuX2? So 0.82, you just check, and then you notice that is 0.45, right? And then based on this, you just need to substitute in the correct numbers lah. Okay, because they tell you the Kc is 2.1, and then you know the H plus concentration, I hope. Okay, do you know that? Right. Yeah, pH 3, right? Okay, then the rest of details, you just sub in, and then you can get the copper 2 concentration to be this, from this. Okay, then based on that, you can go and estimate lah, sort of estimate, right, or calculate the percentage of copper 2 being extracted. Okay, so or the initial amount of copper 2 that remain in the system. Okay, I think either way you do it, the answer will be about the same. So you should get about 99.8%. Okay, would that be alright? I think that should be okay. I think nothing very. I think it's just a novel application of chem equilibrium, but other than that, nothing fanciful. Okay, then okay, so part 4 asks you reference to 4.2, explain how copper 2 can be released. So again, you need to go back to 4.2, right? 4.2 is here. Yeah. How can I release copper 2? So you notice that if I increase the, okay, so there's only a simple way lah, because this is in oil, right? So basically all I need to do is just to up this amount, which is H plus. So you can say you increase the concentration of H plus by adding a mineral acid. Yeah. Copper 2 can be by position of equilibrium shift to the left. Okay, so the student here wrote position. Okay, I think actually this is fine. I think previously can't really see the. Okay, I think this is. Oh, okay, position of 4.2, but okay lah. I think it's contextually is there lah. Okay, I think this one should be able to get a mark. Okay, so just add a mineral acid in, then you shift the POA to the right. I think this is fine. Okay, can. This one you have to be a bit careful. So they say that copper ornaments are tarnished due to copper sulfide. Okay, then usually you can polish them by adding aqueous ammonia. Okay, you need two equations to answer this question. So equation 1 and equation 2. Okay, so equation 1 and equation 2. Yeah, then it is important for you to highlight the shift in the POE. Okay, so basically what you need to say is that, when you apply the aqueous ammonia, yeah, POE of 1 will shift to the right. Okay, so that will cause the POE of 2 to shift to the right as well. So that means that you are removing the copper sulfide from the system. Okay, Then of course to improve on your answer, sometimes it's good to put the phase in, like equals, equals, solids, equals, equals. Okay, then once you put the phase in, I think everything else should be fine. Yeah. Okay, can then I think I'm more or less done.